This is the story of an extraordinary scientific quest. The search for a mysterious volcano that once erupted in the 13th century with extreme violence. One of the biggest eruptions in 10,000 years. Scientists believe the repercussions of the eruption were significant, possibly disrupting the entire planet's climate at the time and causing major impact on human society. But where is this mysterious volcano hiding? For 30 years, scientists the world over tried to locate it, in vain. Yet finding the volcano is crucial. We rarely have the chance to study how large eruptions created climate change in the past, and how they could very well do it again in the future. Today, an international team of scientists has taken up the search, determined to solve the mystery. They're leading a large-scale investigation, traveling across the globe in search of clues, and they've discovered a prime suspect, a monster in hiding. But is it the volcano that erupted all those years ago? It was during a polar expedition that a surprising discovery took place.
The story begins in Greenland, as scientists in the late 1970s were drilling into the ice on the plateau of Greenland and looking back into past climate on the Earth.
This was a multinational project. There were French involved, US, Danish, and Swiss. And two of the really pioneering scientists who were leading this project were a Danish scientist, Hammer, and a scientist from the US named Langway.
The glaciologists planned to analyze the traces of atmospheric gas and particles that had been trapped in the layers of ice year after year over several millennia. By boring into the ice, the researchers could reveal the climate of the past, and they quickly found astonishing amounts of sulfates.
When scientists first started working on the chemistry of the Greenland ice core, they noticed big sulfate spikes in the core, corresponded to major global volcanic eruptions. Some of these include the eruption of Vesuvius, eruption of Agung volcano, eruption of Tambora, eruption of Laki volcano.
The scientists believed that the high qualities of sulfates were the result of a volcanic eruption.
Large volcanic eruptions will pump so much dust and sulfur into the atmosphere that that eventually will rain out over the polar regions. And so you can find a record of past volcanism in the ice cores.
Ice is really a fantastic repository of information about volcanoes because the sulfur that's erupted from the volcanoes is trapped in the ice. So a single ice core can give you information about volcanic eruptions happening all over the world.
Of all the sulfate spikes the team discovered, one had exceptionally high levels. It could well be from the most colossal eruption of the past 10,000 years.
The most prominent of these markers, for several thousands of years, they dated to 1259. And the only way to explain this was that there had to have been a phenomenally large volcanic eruption, but we knew of no volcanic events from that time period.
1259. This massive sulfate spike occurred in the heart of the Middle Ages. The problem was that no eruption had ever been recorded that year. A true mystery. Where could it have taken place? Since the traces were found in Greenland, glaciologists suspected the Northern Hemisphere. But a few years later, in the early 80s, other climate-related drillings were completed on the other side of the planet, in Antarctica. Once again, the scientists discovered something shocking. Glaciologists Joel Savarino and Jean-Robert Petit, who work on climate reconstruction, are repeating the experiment conducted by their counterparts in the 1980s. The scientists pass an electrical current through an ice core that was collected in the South Pole 79 meters below the surface. The ice contains atmospheric particles from 800 years ago in the 13th century, which fell to the ground and were trapped in the ice.
Waouh! Ça, c'est du pic. Ce pic représente un pic de sulfate volcanique. On voit son importance, qui se dégage bien du bruit de fond. Compte tenu de la datation de la carotte, de sa profondeur et de l'importance du pic, on est sûr d'avoir identifié le pic du 1259.
The plot thickens. The same sulfate spike dating from 1259 was found in ice from both the North Pole and the South Pole. Such symmetry is truly exceptional. The scientists are intrigued. Are they traces of the same eruption, or were there several eruptions that took place simultaneously in both hemispheres?
The mid-13th century mystery layer was phenomenal for the amount of sulfur in it. Unfortunately, sulfur doesn't tell us anything really about which volcano produced it. Sulfur is sulfur. But there was something else in the layer that was much more valuable as a clue to finding the volcano, and that was very fine particles of ash. And the ash proves to be very, very important because the ash can carry a unique fingerprint of the magma, the molten rock from the source volcano.
To determine if it was a single eruption or several, the scientists conduct a side-by-side comparison of the tiny particles of volcanic ash trapped in the two poles. Their shapes and geochemical compositions are identical. The ashes thus came from the same eruption, one that must have been gigantic to have generated the massive sulfate spike of 1259. This information gives the scientists new leads in their search.
The fact that you had the event recorded in both polar regions suggested that the eruption had to be somewhere in the tropics. A very high latitude eruption couldn't get its dust into the opposing hemisphere, not so far north or south. So that was a clue, but it was still a huge challenge to identify the volcano responsible because there are so many volcanoes.
Although locating the volcano is a challenge, researchers now have a lead: its traces. Such an eruption must have left traces elsewhere. But where? In northern Quebec, spruces that have been dead for thousands of years are found at the bottom of lakes. Like polar ice, these trees bear witness to the climate of the past. Buried deep beneath the sediment, they were spared decomposition. Using carbon dating, the researchers are able to isolate specimens that grew in the 13th century. Studying the shape and size of the tree's rings may reveal important clues about the climate of the time.
Here in this sample we can see a crack that corresponds to a light ring which formed during a short summer. In the lab we will polish the sample finally, and the end result is something like that. These two rings represent the years from 1240 to 1258, where you can see an abrupt decrease to temperature. We have sampled more than 2,000 trees in 6 lakes, and when we analyzed all these data, we noticed some abrupt changes in tree growth, and the most significant was in 1258. It's not just here in North America, because we know from other treeing evidence that this was also a cold year in Mongolia, for example, and thus it was probably a global event.
The trees have revealed their secret. A sudden planet-wide cooling took place in 1258. Was it connected to the mysterious eruption? In Paris, at the Laboratory of Oceanography and Climate, climatologist Miriam Caudry is looking for the answer. She and her team studied the impact of the most powerful eruption of the 20th century, Mount Pinatubo in the Philippines in 1991. Their modeling helps them understand how a stratospheric eruption can affect the climate of the entire planet.
On sait que les éruptions stratosphériques, c'est-à-dire qu'il y a une colonne éruptive qui va très haut dans l'atmosphère, ont un impact sur le climat. Pas parce qu'elles éjectent des roches ou de la lave en fusion, mais parce qu'elles dégazent du soufre. Ce gaz soufré va être injecté très haut dans l'atmosphère par la puissance de l'éruption. Et le soufre, une fois qu'il atteint 20 km, il va subir tout un tas de réactions chimiques, notamment avec la vapeur d'eau.
In the stratosphere, Sulfur dioxide molecules mix with water to form a suspension of billions of microdroplets of sulfuric acid, aerosols.
Ça va avoir pour conséquence de réfléchir comme un miroir ces rayonnements solaires vers l'espace. Or, le rayonnement solaire, c'est ce qui fait notre climat, c'est ce qui nous chauffe. Eh bien, très vite, on va avoir un impact climatique.
This gigantic mirror effect diminishes sunshine, thus cooling the average temperature on Earth. But that's not all. Up in the stratosphere, aerosols absorb the infrared rays emitted by the sun and the Earth. This heats up the stratosphere, which in turn upsets the trajectories of the planet's strongest air currents and creates meteorological chaos on Earth. In modeling the Pinatubo eruption, Miriam discovered an unexpected clue: the date of the mysterious eruption.
Le fait que le cycle de vie du voile d'aérosol est de 3 ans pour Pinatubo, on le sait parce qu'on l'a observé, nous a permis de remonter finalement dans le temps et dater le début de l'éruption mystère en 1257.
This means 3 years passed between the mysterious eruption in 1257 and its ashes falling on the poles in 1259. Using the year 1257 and the characteristics of the enormous sulfate spike, Miriam modeled the climate effects of the mysterious eruption.
Très vite, on voit l'impact sur le climat et en particulier, on a eu un refroidissement majeur d'abord dans les tropiques, là où le voile d'aérosol s'est formé. Et ensuite, cette anomalie de température froide se propage, on peut voir à l'échelle de la planète. Et notamment, l'année d'après, l'été 1258, on a constaté que nos modèles simulaient un été froid, jusqu'à moins 1 degré Celsius en Europe de l'Est, en Europe de l'Ouest et en Angleterre, à nos latitudes.
A rapid planet-wide cooling of even 1 degree Celsius over a few months would have dramatic consequences. Researchers believe it would have devastated the medieval societies of the time. But where's the proof? It's in the heart of London that an extraordinary discovery would reignite the case. In 1999, a market construction site in Spitalfields unearthed a large cemetery that contained hundreds of mass graves. Archaeologists dug up over 10,000 skeletons that dated back to the Middle Ages, a truly exceptional find. Osteologist Don Walker participated in the excavations.
Mary Spittal really is unique. Some sort of catastrophic episode has killed a lot of people in a very short space of time. In some circumstances we found 20 or even up to about 40, 45 individuals just in one single pit. And it was a real surprise, and what we wanted to do was find out what's going on here.
Researchers explored several possible causes of death, starting with the Black Death in 1348.
We looked at this. We did radiocarbon dating to check the dating of the cemetery. I mean, we actually found that most of them came out about 100 years earlier, in the mid-13th century.
The Black Death ruled out, scientists explored the possibility of the graves being from a military battle. But of the 10,500 exhumed skeletons, only one showed signs of a fatal blow. And scientists also found proof of something else.
Half of the people in the mass burial pits are females. In a battle grave, you'd expect to find mostly males. So in the absence of this kind of injury in the mass burial pits, we have to say that they are not from battle.
So, what could have killed all these people?
The only thing we could really find in the mass burial pits that was different was that they had lesions on the teeth, which suggests that the people who were dying were those who were weakest, who had suffered malnutrition in the past, and they were more vulnerable to disease and famine in later life. So their immune systems are not working properly. You get opportunistic infections such as influenza or measles that go through a population very quickly.
A terrible famine would have therefore struck London in the middle of the 13th century. Was it somehow connected to the mysterious eruption? Writing being well developed in the Middle Ages, Don Walker headed to the British Library for clues and focused on one particular manuscript from the middle of the 13th century, the Chronica Majora.
From about that time till the end of March, the north wind blew without intermission. A continued frost prevailed, accompanied by snow and such unendurable cold that it bound up in the face of the earth, and that led to the deaths of many animals and the failure of crops. This is a very important manuscript for us because it's written by Matthew Paris, a monk who lived in St Albans in the 13th century, and he described basically what was going on in London, especially in 1257, 1258. So that's key for our investigations.
Matthew Paris described what happened in the summer of 1258.
Owing to the scarcity of wheat, a large number of poor people died, and dead bodies were found in all directions, swollen and livid, in the muddy streets. When several corpses were found, large and spacious holes were dug in the cemeteries, and a great many bodies were laid in them together. And this is exactly what we'd expect in times of famine, when in fact it's not the food shortage itself that kills people, it's the fact that infectious disease runs rife. All they want to do is bury them as soon as possible to prevent this disease from spreading, and so they have to dig these huge pits.
The population of London was hit hard by the effects of the eruption. The famine of 1258 was one of the worst ever recorded in England. Matthew Paris mentioned 15,000 deaths. That means 30% of the British capital's inhabitants disappeared that fateful summer. If London wasn't spared, could other places in the world have experienced such loss of life? Historian Sébastien Guyet has visited numerous monasteries and libraries across Europe. Here too, it's thanks to accounts recorded in monk manuscripts from the 13th century that he found precious clues.
L'Angleterre n'est pas le seul royaume touché par la famine. Les sources historiques attestent de sévères crises de subsistance dans presque toute l'Europe. C'est le cas en France, en Espagne, en Allemagne, de 1258 à 1261.
Among the most significant texts found by the historian was this inscription in the Annals of Speyer in Germany.
Maxima fuit corruptio, vini et frumenti, et aliarum frugi, et appellatus es anni idem vulgo munceliar. Tout le texte est écrit en latin, à l'exception d'un seul mot, munceliar. Ce terme signifie non seulement l'année sombre, mais également l'année des brouillards. Il a été inventé par la population, une population qui a dû souffrir pendant plus d'un an d'un manque de soleil constant, de très mauvaises conditions météorologiques, tant au niveau des températures que des précipitations. Et l'année des brouillards suggère très fortement qu'on avait la présence d'un voile d'aérosol volcanique dans la stratosphère en 1258.
This dark year didn't only concern the European continent. Other accounts prove it affected the rest of the world as well.
À l'autre bout de la planète, à la même époque, le Japon est lui aussi affecté par une terrible crise. C'est ce que nous apprennent le moine bouddhiste Nichiren et aussi le manuscrit de l'Azuma Kagami, qui tous les deux décrivent des températures très froides pendant l'été 1258, des pluies diluviennes et une famine très importante qui va se traduire par des milliers de morts.
Following the traces of the mysterious eruption revealed that from Europe to Asia, the eruption caused total climactic chaos and took tens of thousands of lives. But the mystery still lingered. Which volcano?
With all the evidence that was amassing from the ice cores, from the tree rings, from the chronicles, all points to a large explosive eruption should have left a large crater behind.
The culprit hence looks like a giant crater and is equidistant from both poles, in the tropics. That means it's hidden among hundreds of other volcanoes over thousands of square kilometers. It's a needle in a haystack. Yet starting in the 1980s, the search for the mysterious volcano galvanized the scientific community. Multiple volcanoes were declared suspects, like Quilatoa in Ecuador. But another name also came up, the terrifying El Chichon in Mexico. Its monster eruption in 1982 was both explosive and stratospheric.
El Chichon became a really good candidate because when El Chichon erupted in the 80s, it was a very sulfur-rich eruption, and the sulfur from that eruption from El Chichon circled the globe. And also, El Chichon was known to have erupted more or less in the right time frame.
Cette éruption a fortement marqué les esprits des volcanologues et des climatologues, d'autant plus que la composition chimique du Chichon avait des similitudes avec les premières analyses des fragments volcaniques trouvés dans les carottes glaciaires associés au pic de sulfate de 1259. Le problème avec l'hypothèse du Chichon, c'est que l'éruption de 1360 du Chichon, plus ou moins 100 ans, a produit 1 km3 de magma. C'est un volume très petit, beaucoup trop petit pour avoir occasionné le plus grand pic d'aérosol sulfaté des derniers millénaires.
Looking at the intensity of the 1259 sulfate spike, volcanologists estimated that the mysterious eruption ejected around 40 cubic kilometers of magma. That's around 40 times more than the terrifying El Chichon. The Mexican volcano was officially off the suspect list. The wanted monster was much, much larger. Over the next 20 years, the search seemed to reach a stalemate. That is until two researchers, Frank Levine and Jean-Christophe Komarovsky, decided to reopen the case in the early 2010s.
On avait en fait peu d'informations, mais des informations déjà importantes. On recherchait une éruption explosive d'une telle magnitude qu'elle avait dû certainement engendrer la formation d'un énorme cratère de plusieurs kilomètres de diamètre, des carrières de ponce, qui sont les produits classiques typiques d'une éruption explosive de grande magnitude.
Croiser la taille de la Caldera avec des carrières de ponce, la présence de pierres ponces en grande quantité, rien que ce croisement-là apporte vraiment beaucoup d'informations. Et donc ça a été vraiment le point de départ pour aller cibler certaines zones, certains volcans.
Combining these two clues, the crater size and the pumice stone sediments resulting from a massive explosive eruption, the two scientists started their search by exploring satellite images.
On a essayé de chercher dans des régions qui n'avaient pas contenu les 3 ou 4 volcans qui étaient les premiers suspects.
En Amérique, les volcans sont pas mal étudiés. En Afrique, il n'y a pas de volcans qui correspondent à ce type d'éruption.
Et donc, on a naturellement focalisé sur l'Indonésie, qui est le deuxième pays au monde par sa quantité de volcans actifs, avec des volcans qui n'étaient pas connus.
The Indonesian archipelago is home to 129 active volcanoes, including the illustrious Merapi and others known for past eruptions, Krakatoa, Toba, and Tambora. What's unique about this archipelago is that it was formed by a highly active subduction process. The southern Indo-Australian plate still descends 7 centimeters a year beneath the northern Eurasian plate. Far below the surface, the Earth's water-laden crust melts, generating large pockets of molten rock called magma. It then rises to the Earth's surface in magma chambers, powering eruptions in the Indonesian archipelago. The volcano we seek could very well be hidden in the middle of this cluster.
Il y en a de partout, des volcans ici, tout du long. Nous, on cherchait une énorme éruption, ça veut dire une caldeira de plusieurs kilomètres de diamètre, de la taille de Tambora par exemple. Au niveau de l'échelle, là, on est à combien, 6 kilomètres par là?
6 kilomètres, oui, à peu près, hein, 6 kilomètres et 1 kilomètre de profondeur.
C'est magnifique celle-là.
Frank and Jean-Christophe prepare a list of suspect volcanoes that have both a large crater and pumice stone sediments. These are yet unexplored and undated, nor have they been geochemically analyzed.
La première région qu'on a décidé d'aller voir, c'est Sumatra, parce qu'on sait qu'il y a des pierres ponces en grande quantité. On a des carrières assez impressionnantes, notamment dans la région qui s'appelle Lampung, en face de Krakatoa. Et le petit point blanc qu'on voit ici, c'est une très grande carrière de ponce qui fait à peu près 1 km de long sur 500 mètres de large. Donc avec mon collègue indonésien Indio Pratomo de la Geological Agency, on est allé sur le terrain pour échantillonner dans cette carrière. Mais très vite, on s'est rendu compte que ces ponces étaient très dures, très indurées, très agglomérées, et donc apparemment bien plus anciennes que celles qu'on recherchait du XIIIe siècle.
Additional suspects have been eliminated, but one island neighboring Bali has caught the researchers' attention, the island of Lombok.
C'est une île qui rassemble un peu tous les critères qu'on recherchait. D'abord, une très jolie caldeira et surtout très grande caldeira, qui est à peu près de la taille de celle de Tambora, 6 km de diamètre par 8. Et surtout, deuxième critère fondamental, l'île est elle aussi recouverte de ponces, mais en beaucoup plus grande quantité qu'ailleurs. Il y avait quand même un problème majeur, c'est qu'officiellement, sur la carte géologique, cette caldeira, elle était datée de plus de 10 000 ans. Mais en regardant de plus près la morphologie, qu'on voit bien ici avec des arêtes très vives, on se rend compte que c'est beaucoup plus récent.
Doubtful of the volcano's dating, Franck and Jean-Christophe decide to follow their intuition. They head to Lombok, accompanied by Indonesian scientists. Their goal is to explore the volcano that overlooks the island, Mount Rinjani, searching for clues that would allow them to date the eruption and quantify the volume of its sediments. Is this mysterious crater where the 40 cubic kilometers of mysterious volcanic material came from?
On se trouve devant un immense cratère d'origine volcanique qui mesure 6 km par 8 km. Et en fait, ce cratère, c'est une caldeira qui s'est formée lors d'une éruption explosive suite à l'effondrement du volcan sur lui-même.
The original volcano no longer exists. Nothing remains but this enormous caldera. What led to this incredible transformation? Several kilometers beneath the volcano, magma accumulated in the magma chamber. The gases dissolved in the magma put immense pressure on the entire structure. The volcano began to erupt. Gases and magma were freed in an immense rising column that partially emptied the magma chamber and weakened the walls of the volcano. It collapsed over itself. Millions of tons of rock fell into the magma chamber, leaving in their wake a giant open crater, the caldera. Jean-Christophe goes into the caldera to take a site reading. He meets up with Devi Kamil Siabana and his Indonesian volcanology team, who are responsible for observing all the volcanoes in eastern Indonesia. Devi and his team closely monitor Mount Rinjani, its immense caldera, and its two other craters. An extinct volcano at an altitude of 3,726 meters, and the Barujari, a very active young volcano at the very center of the caldera. Mount Barujari is like a window into the magma chamber, located 4 kilometers beneath the surface of the caldera. To measure its evolution, volcanologists take gas and lava samples from the Barujari's most recent flow. All signs indicate the magma chamber is filling up. This is confirmed by another clue, the water temperature of the lake that formed over the caldera.
Normally for a lake with an altitude of 2,000 meters above sea level, we will have like 14 to 15 degrees Celsius. But here at Tagaranak Lake, we have a 20 to 22 degrees Celsius, which indicates a very strong magmatic activity beneath the caldera.
A considerable amount of energy is still accumulating beneath the caldera, putting the young Barujari under constant pressure. Jean-Christophe is convinced that the Rinjani's caldera is the remains of a gigantic eruption, just like the one they've been searching for. Could it be from the eruption of 1257? To find out, the scientists decide to examine the very thing that could help them understand more about the volume of the eruption: the pumice stone sediments. The satellite images seem to indicate sizable sediments in the area. But Franck and Jean-Christophe didn't expect to find such a large one more than 25 kilometers from the volcano.
belle ponce, hein. Ouais. Ce sont des pierres ponces, et en fait ce sont des fragments de magma consolidés qui proviennent de l'immense éruption explosive qui a formé cette caldeira. Et on les retrouve aussi dans des coulées pyroclastiques qui ont nappé en fait tout le paysage ici sur des dizaines de mètres d'épaisseur et sur des centaines voire des milliers de kilomètres carrés.
Pyroclastic flows are an extremely destructive volcanic phenomenon that's characteristic of explosive eruptions. These avalanches of gas and smoldering volcanic debris, including pumice, hurtled down the volcano's sides for dozens of kilometers. These pumicestone sediments are the remains of the pyroclastic flow. Studying them reveals another precious clue about the date of the eruption.
Ouais, ça c'est pas consolidé du tout. Le fait que ces matériaux soient très peu consolidés, alors qu'on est en milieu tropical humide, montre que l'éruption est assez récente. Elle ne peut pas avoir plusieurs milliers d'années. Et vu l'ampleur des dépôts tout autour de l'île, ça montre bien qu'on a un candidat quand même sérieux pour l'éruption mystérieuse de 1257.
The discovery of charred tree trunks in the pyroclastic flow confirms the scientists' initial impressions. Their carbon dating indicates a time frame between 1163 and 1264. Pumicestone sediments as remains of a gigantic explosive eruption, carbon dating confirming a 13th century time frame, and a huge and still active caldera. All these signs make Lombok seem exceptionally promising. Jean-Christophe and Franck decide to go deeper into their investigation, accompanied by their colleague Indio Pratamo, an Indonesian volcanologist. On the north side of the island, 30 kilometers from the volcano, a 35-meter-high pumice cliff has caught their eyes. They want to know if the global volume of the pyroclastic flows could match the 40 cubic kilometers of material previously estimated.
Ça, on a des litiques, hein?
Ça, c'est un litique, le gros, comme ça.
C'est le gros litique.
Il y a beaucoup de lithique hein, dans ce dépôt.
Lithic fragments are rocks from the volcano's walls. Their high concentration in the sediment reveals a clue. This flow formed towards the end of the eruption, when the volcano was collapsing and becoming the caldera. This eruption created enormous quantities of pyroclastic flows until the end, but figuring out their overall volume will be extra tricky.
La coulée sur laquelle on se trouve se prolongeait sur peut-être 1 ou 2 kilomètres en mer, puisqu'à l'heure actuelle, il y a encore 35 mètres de falaise. Et d'après les témoignages locaux, il y a encore quelques décennies, la falaise était à 500 mètres plus en mer.
Part of the pyroclastic flows disappeared into the sea. A map of their spread over the island confirms the magnitude of the eruption. But how can they calculate the overall volume of all the pyroclastic flows?
Une des grosses difficultés dans ce genre d'études, c'est d'essayer de reconstituer le volume total de matériaux de l'éruption. Un des moyens, c'est de faire une sorte de portrait robot de cet ancien volcan avant justement qu'il ait été complètement déformé et décapité en quelque sorte.
The answer is back in Paris, at the Department of Geosciences at the University of Paris-Sud, where geomorphologist Pierre Lahitte made a 3D model of the volcano before it collapsed over itself.
À partir de la topographie disponible grâce à des données satellites, on a recherché quels étaient les secteurs du volcan actuel qui étaient en fait des morceaux préservés de l'ancien volcan. Les points violets correspondent à l'élément de surface du Rinjani, et puis tous les points noirs appartenaient à un volcan sans doute bien plus grand, peut-être plus haut, qui est aujourd'hui le lieu de la Caldera.
The mathematical modeling proves there was actually not one, but 2 volcanoes.
Le Rinjani, qui est toujours présent, mais qui culminait à l'époque à 4100 mètres. Et à côté de lui, un autre volcan bien plus vaste, plus haut, culminant à 4200 mètres, et qui est aujourd'hui le lieu où se trouve l'énorme Caldera.
After accounting for the water volume of Lake Segara Anak, the volume of the young Barujari, and that of the collapsed Rinjani in the Caldera, Pierre Lahitte calculated that this great volcano lost 2,800 meters in height and ejected 40 cubic kilometers of material during its eruption. A mind-boggling quantity that means this eruption was one of the most violent ever. A magnitude 7, equivalent to 100 times the strength of the Pompeii eruption. The computer profile confirms that the volume of the Lombok eruption matches the mystery eruption. But this new evidence reveals another problem. There's a second volcano, one that isn't on any map, which scientists now need to study. Thanks to his Indonesian contacts, Frank Levine learns that the museum in the capital of Mataram houses some precious texts, the Babads. These historical and legendary texts, carved into palm leaves and written in Old Javanese, are many centuries old. Among the 1,300 Babads preserved at the museum, one is particularly intriguing.
Ini adalah naskah Babad Lombok yang menceritakan tentang sejarah Lombok dari zaman prasejarah sampai zaman sejarah. Isinya salah satu adalah tentang Gunung Rinjani meletus. Gunung Rinjani longsor dan Gunung Samalas runtuh. Banjir batu gemuruh menghancurkan desa Pamatan. Rumah-rumah roboh dan hanyut terbawa lumpur. Sebagian penduduk mati tenggelam dan sebagian lagi lari ke gunung-gunung. Kemudian punah seluruhnya ditelan gelombang.
Ce qui est remarquable avec cette Baba de Lombok, c'est qu'on a découvert à travers ce récit qu'on a un volcan inconnu jusque-là qui s'est effondré, le mont Samalas, alors que jusque-là on appelait le volcan le Rinjani et on considérait qu'il n'y avait qu'un seul volcan.
Thanks to the Babad, scientists are finally able to name their primary suspect, the Samalas. But that's not all.
Ce qui est fantastique aussi dans cette Baba de Lombok, c'est qu'elle mentionne l'existence de Pamatan, qui est une ancienne capitale d'un royaume jusqu'alors inconnu. Et cette capitale a été détruite pendant l'éruption, par l'éruption, et gît sans doute quelque part sous les pierres ponces à Lombok.
Archaeologists may someday find the remains of Pamatan, believed to be the Pompeii of Southeast Asia. But in the meantime, a third clue has caught the geographer's attention.
Parmi les effets locaux de cette éruption, on peut aussi soupçonner la présence de tsunamis, parce que dans la Baba de Lombok, il y a une description de ce qui ressemblerait à un tsunami causé par l'entrée des coulées dans la mer.
A tsunami of volcanic origin can be extremely destructive. If they can prove it took place, the scientists will have an even deeper understanding of the eruption's local and regional impacts. This task fell to Patrick Vosmer, a worldwide expert on tsunamis. Accompanied by Indonesian oceanographer Bakhtiar Mutakin from Gadjah Mada University in Java, he began searching for clues on the west coast of the neighboring island, Sumbawa. This area is directly across from the point of impact of the pyroclastic flows that occurred east of Lombok. Here, the two islands are separated by a mere 15 kilometers.
On a tenté une simulation à partir de l'arrivée des coulées pyroclastiques, définies par les volcanologues. Ouais. Et si tu regardes, je vais lancer la simulation, on voit bien ici que les coulées pyroclastiques poussent la mer, génèrent des vagues, et là, l'onde commence à ralentir. Ouais. C'est quand le plancher de l'océan commence à remonter. Et comme elle se ralentit, elle se contracte, elle devient plus étroite, voilà, et elle augmente en niveau.
C'est ça.
Et du coup, je pense qu'on a des vagues qui déferlent sur cette zone littorale.
Does any trace remain of the tsunami that would have surged towards the local coastlines hundreds of years ago? It's at an abandoned shrimp farm that the scientists finally find an exposed outcrop.
Là, on a du sable, et ce sable-là, c'est du sable, tu vois bien que c'est du sable marin, parce qu'on a des tout petits morceaux de coquilles. Ici, de coquilles. On a bel et bien une couche, là, très nette, de galets, donc c'est le front de la vague. Ensuite, on a de nouveau ce gros niveau avec des pavés qui font 20 cm de grand axe, et de nouveau du matériel fin. ce serait la deuxième vague. On retrouve 3 vagues qui sont assez bien différenciées, avec toujours le front de la vague qui est très turbulent et qui va déposer des éléments grossiers. Ensuite, du matériel plus fin. Et puis là, on repart avec une séquence qui va de là à là, avec du grossier, le front de la vague, et du fin, la queue de la vague. Et on recommence encore une fois. Donc c'est un dépôt de tsunami où on a 3 vagues qui sont clairement identifiées.
The eruption led to 3 waves that submerged the Sumbawa coastline. But using a simulation, the scientists discover another tsunami of much greater scope. When it uses North Lombok as the location where the pyroclastic flows entered the sea, the simulation reveals that other waves would have devastated the coasts of Bali and of all surrounding islands for thousands of kilometers, likely taking many lives with them. The ideal predator is slowly revealing its secrets. But the scientists still need to prove that the Samalas eruption was what caused the enormous sulfate spike of 1259. To do so, they must prove the eruption reached the stratosphere and formed a giant global aerosol suspension. It's now the volcanologists' turn to study the outcropping on Sumbawa Island. They're looking for materials that were projected to far distances.
Cette ligne blanche là, c'est très marqué.
Oui, oui, oui. Alors.
Là, là, partout.
Bon.
Et alors, contient quoi ça? C'est quoi ça?
Voilà, des vraies ponces, hein?
Ouais.
Ouais.
Des ponces bien blanches.
Ouais, bien blanches.
Ouais, c'est des belles ponces. Hein.
Des ponces, là.
Des belles ponces à cette distance, à 56 km de distance du volcan. Elles ont voyagé contre le vent.
Oui,
hein.
En plus.
Et elles sont encore de grosse taille. Et on a des fragments arrachés au volcan aussi, hein, des petits fragments noirs qui sont plus denses.
Là, oui, c'est vrai, lithique là.
Their inventory of pumice and lithic fragments found far from the volcano allowed them to map the spread and the thickness of the eruption's airfall. The affected area is enormous. The pyroclastic falls would have covered thousands of square kilometers around the volcano, perhaps even more than 600 kilometers west of Java, where, on the edges of the Merapi, a 2-centimeter pumice layer was identified as being from the Samalas. But what will really determine whether the eruption column reached the stratosphere or not will be the size of the fragments found on the ground.
La taille de ces particules nous permet de déduire la hauteur atteinte par cette colonne, parce qu'on sait que pour les fragments d'une même taille ou d'une même densité, plus ils sont éjectés loin du volcan et transportés loin du volcan, plus le panache qui les a transportés a atteint une altitude élevée.
Did the Samalas plume reach the stratosphere? Based on the fragments that were found in the area, the height of the smoke plume was absolutely stupefying. 43 kilometers. That's the highest plume of smoke ever recorded. The eruption of the Samalas was clearly stratospheric. But did it inject enough sulfur dioxide into the atmosphere to have created the large sulfate spike of 1259? The problem is that all the gases vanished during the eruption. How can one quantify something that no longer exists? It's at the Institut de Physique de Globe de Paris that researchers found the answer, in the tiny crystals encrusted in the very heart of the pumice stones. Once cut into thin slices, these crystals revealed their treasures, melt inclusions. These are tiny drops of magma trapped within the crystals, which retained their gases in spite of the eruption.
Quand le magma était mis en surface, il a perdu la quasi-totalité de ses gaz. Donc si on veut retrouver la composition de ces gaz quand ils étaient encore dissous dans le magma, eh bien il faut aller étudier ces inclusions vitreuses qui vont nous donner l'histoire de ce magma et de cette phase gazeuse depuis la zone de stockage jusqu'à la surface.
By cross-referencing the 40 cubic kilometers of projected magma with the concentration of sulfur present in the crystals, the scientists are able to calculate the total amount of sulfur dioxide emitted by the Samalas.
On a calculé pour la première fois que cette éruption a produit 158 millions de tonnes de dioxyde de soufre. ce qui est une quantité phénoménale et probablement la plus importante dans les derniers millénaires.
158 million tons of sulfur dioxide, nearly 2 times the volume emitted by the eruption of the Tambora in 1815, which up until now had been considered the largest eruption of the last few millennia. This volume corresponds to the intensity of the sulfate spike of 1259. All evidence points to the Samalas as the source of the mysterious eruption. And yet, one final obstacle could still change everything. In the laboratory of glaciology in Grenoble, the ash microparticles found in the South Pole have been carefully prepared so they can be compared to those from the Samalas. These microparticles are so fine that handling them requires an environment completely free of any outside dust. It's a delicate operation. The micro-ashes must be separated from the aerosols present in the sulfate spike of 1259 and from every other speck of dust that was present in the atmosphere at that time. The final step is carried out at the Institut de Physique de Globe de Paris. Compared side by side under an electronic microscope, the two samples found thousands of kilometers away from one another will reveal that they share the same origin. On the right, the ash from the South Pole. On the left, the ash from the Samalas.
Sur ces écrans, on observe des particules de taille identique, de 3 à 4 microns environ. Et on observe également que les surfaces sont très homogènes sur les deux particules de cendre et que les bords sont très saillants. Et cette première observation, elle nous permet de dire que les morphologies de ces deux cendres sont très similaires.
The shapes match. Now for the last and final comparison, geochemical fingerprinting.
Sur ce diagramme, on voit les pics d'intensité de chaque élément chimique qui est présent dans la cendre du pôle sud. Par exemple, l'oxygène, le sodium, le magnésium, l'aluminium ou le silicium.
The chemical composition of the Samalas ashes appears in blue. The two diagrams are identical.
Ces deux cendres, elles ont non seulement des formes similaires, mais en plus, elles ont des compositions chimiques qui sont comparables à plus de 99%, et c'est vraiment excellent, et ça permet de conclure qu'elles ont la même origine.
The many different clues are finally all coming together. The Samalas is definitely the volcano responsible for the giant eruption of 1257. In the field, Jean-Christophe Komarovsky even found a wall that displays the entire eruption process.
From here on to about the top of this cliff is the 36-hour eruption sequence summarized. This brown layer here is the ground layer at the time of the eruption in 1257, where people were farming and living and walking.
In 1257, under massive pressure from the gas accumulated in its magma chamber, the Samalas exploded.
The first phase of the eruption is basically an intense rain of pumice for 6 to 7 hours from a very tall eruption plume, similar to the Pompeii eruption, but on a much, much larger scale. Then you notice here a second layer formed by a turbulent pyroclastic flow, an avalanche of incandescent fragments and gases, but very turbulent, perhaps 200, 300 kilometers per hour, sweeping down the flanks of the volcano, reaching this location at 25 kilometers from the volcano. And then we have the third phase of the eruption. Again, we get about 6 to 8 hours of continuous rain down of pumice fragments. And then we get the fourth phase, the final climactic phase of the eruption. You get such a high flux of material coming out that it cannot sustain the column, and the other phase, the volcano is collapsing on itself, and it continues to erupt for several hours, a sequence of these pyroclastic flows devastating the whole area.
It only took this enormous volcano a few hours to radically change the course of the world. And it was thanks to great persistence that scientists were able to solve one of the greatest mysteries our planet has ever known. The Samalas is now a part of history.
It took so long to solve this mystery, and I'm not that surprised it took so long. In fact, I'm surprised that we eventually found it, because there are so many volcanoes around the world. There are even ones with calderas that are hidden beneath the sea that could be responsible for some very big events in the past. So I think we were actually quite lucky to find out that Samalas was responsible for this huge event in the mid-13th century.
Yet the Samalas still harbors many secrets.
On n'en est qu'au tout début des investigations dans le domaine de l'histoire locale, de l'anthropologie, de la topographie. Et notamment, le plus gros challenge, c'est sans doute dans le domaine archéologique, parce que le royaume de Pamatan est encore enfoui sous les ponces.
Could Pamatan be the Pompeii of Southeast Asia? Answering will be one of the next challenges. With their Indonesian physicist colleagues, Frank Levine and his team have already discovered that 760 years ago, the shoreline was more than 2 kilometers back from the current coastline, right in the middle of the old Mataram Airport runway. In the meantime, the clues gathered about the Samalas eruption could help envision the future.
Si une éruption explosive de très grande ampleur, du type de celle de 1257, avait lieu demain, elle aurait certainement des conséquences à la fois locales, régionales et globales dévastatrices, notamment du fait que les sociétés modernes sont beaucoup plus interconnectées qu'au Moyen-Âge et que la population du monde a explosé depuis le Moyen-Âge.
This could impact the global food distribution system. There'll be winners and losers. There'll be parts of the world which are very reliant on imports of grain that might be very severely hit. There'll be huge disruption to global aviation, something of course that didn't exist in the 13th century. There'll be disruption of shipping. There'll be huge regional impacts. Wherever this next event of this scale happens, could have a huge impact on markets that could trigger another global economic crisis.
Only after a global study that began more than 30 years ago did the Samalas finally reveal its secrets. This discovery gives us an exceptional opportunity, a chance to better understand the impacts of large-scale eruptions on the entire planet's ecosystem. How would we deal with one today? Because an eruption like the Samalas could happen sooner than we think.